All right, good morning, everyone. All right, so any questions? I finished up last time with, gave you a couple of bonus problems, and I let you all work on those together. I don't want to cover these because they're bonus problems, but I'm going to do a few more polynomial functions today. So maybe after I do a few more of those, it'll help you with these. So other than these questions, do you have anything for me today? Any questions? Abigail Ruiz? Abby Ruiz?
Yes.
Do you have any questions, Abby?
No, sir.
Okay. All right, well, in that case, let me continue with polynomial functions. We established last time kind of a set of steps. These were our steps from last time, and I'm gonna just follow these. Let me see, we did that example yesterday, and then I gave you the two to do on your own. So let me just go ahead and give you something new. Okay, how about this? F of X is equal to, let's go X to the 6th minus 3X to the 5th. Then let's go hey, let's just do that. Let's just do that right there just to get us started today. So this is a polynomial function because we have powers on the x's that are non-negative integers. We talked about that last time. So the first step in this process, can somebody tell me what the first step is?
Determine the end behavior.
End behavior. Okay, so to determine the end behavior, we're going to look at the degree. Okay, the degree of this polynomial is the highest power of x that we see, which in this case would be 6. And 6 is an even number. So that's what we're looking for. When you talk about the degree, we're looking at whether or not it's even or odd. And then we look at the leading coefficient, LC. That's the number in front of the highest power of x, which is 1, and that's positive. It's greater than 0, so positive. And that means that we will go to that table I gave you last time, this one right here, the leading coefficient test, and we're going to look for an even degree, which is here, and a positive leading coefficient, which is here, so we're going to be the yellow one here. So we know that the left side and the right side of this polynomial should go up. And we're left to figure out what happens in the middle. So in the middle, what do we do? Somebody else? How about Victoria? Is Victoria around? I see you there. Victoria. No Victoria, going once, going twice. Sold. Okay, how about Min? Min, are you there? Going once, going twice. Okay, how about Alexis?
I'm here.
Okay, so Alexis, the second step, you remember what that is?
You find the X-Intercepts.
Okay, X-Intercepts. Do you remember how to do that?
Let me see.
Free to look through your notes.
You find like the greatest common factor.
Okay, so you're starting to do something now, but you have to take the original function, okay, the polynomial itself, and set it equal to 0. Okay, that's how we find the x-intercepts. Then that's when you would start by trying to factor the left-hand side. So you would pull out a greatest common factor. Alexis, do you see a greatest common factor, something that occurs in both of those?
X fifth.
X to the fifth. So if we pull that out, what would we be left with in that parenthesis, Alexis?
X minus 3.
There you go. Okay, good. All right, anybody have any questions on that? So far, we're okay? Now what we do is we take each of these factors and we set them equal to 0. So we have two different equations we're going to wind up solving here. The first one, oh, I forgot to put equal 0 there, sorry. The first one, x to the fifth equals 0. Well, that is more of just a mental thing. You just think about it. What number do you have to raise to the fifth power to get 0? The only number that would work would be 0 itself. So that solution I'm getting just by kind of thinking through it. The other one, I just do some algebra. I just add 3 to both sides, and I get a solution of 3. Okay, so these are the x-intercepts that we have for this graph. Let's see, Sammy, you around, Sammy?
Yes.
Hey, Sammy, do you remember what we do next?
Is it to see if they like touch or cross?
Exactly. We have to see if they touch or cross. So do you recall how we do that?
Yeah, so if it's even, if the number is even, they touch, and if it's odd, they cross.
Okay, so I agree. If it's even, we will touch. If it's odd, we will cross. But what number are you referring to? Are you referring to these numbers? Am I looking at those to see if it's even or odd? Or am I looking at something else?
It's the x to the fifth, the number in.
Okay, good. So that is the most common mistake. I think I mentioned this last time. Most common mistake is that people will look at these numbers and say, is it even or odd? That has nothing to do with the touching or the crossing. It comes from going back up to where you factored it and looking at each of the factors. So this x to the fifth, that's where we got the 0 from. We have to look at the power on that x, which is a 5. That is an odd number. And odd means we cross. Now, what we're doing here, if you go back to last class in our notes, we're doing the part B of step 2. We're determining the multiplicity of each factor. The important word there is of each factor. We're not looking at the x-intercept, the number itself. We're looking back up at the factor itself. So we look at this factored, we look at the 5, it's odd, we cross. Okay, now we have to look at where the 3 came from. The 3 came from this factor, and we have to look at what the power is on that factor. And since there's not a number here, we have to understand that there's a 1 there. And because it's 1, well, that's odd. And odd means we will cross. Okay, so we know that at both x-intercepts, we're going to cross. Okay, let's move on to the next person in line here. How about Justin? Justin, you there? Going once.
I have a quick question.
Yeah, go ahead.
So the coefficients you use to do the odd and odd thing, before I thought we did that step on the equation above, like the main equation.
I'm not quite sure what you mean.
Like the x to the 6 minus 3x to the 5th.
Uh-huh.
Like I thought we did it off that equation to see what was odd and even.
Okay, yeah, so we were doing something with the 6 here, right? The 6 and the 1. What we were doing there was to determine the end behavior. So that's step 1. By looking at those two things, we can tell what the ends of the polynomial do.
Yeah, I got that part. It was just
Okay.
for step 2, or for step 2.
Uh-huh.
Like how we find if it touches or crosses. I thought we did that to the top equation.
To this one?
Yeah.
Okay, this form right here of the equation is not factored because there's a minus sign between these, right?
Yeah.
We have to factor it first. So now what we have here, I'm going to really exaggerate this. We have a dot between those two now, right? We have multiplication. And so when you have two things multiplied together, each one of those is called a factor. And so when you're determining the crossing and the touching, you always want to look at the factored form of the equation. You do not want to look back up here. And the reason you need the factored form is because you need to know which factor goes with which x-intercept. Like I know that the 0 here, right, comes from that factor. If I was looking back up here, I wouldn't know where the 0 is coming from. Is it coming from the one on the left or the right?
Oh, okay. Got it.
Does that make sense?
Yeah. Okay.
Okay.
Thank you. Sorry
You're
about
welcome. Does anyone else have a question? Okay, so Justin, I saw someone send something in the chat. Let me just see what this said real quick. Okay, I got you, Justin. All right, so let's move on to, let's see, Faith, are you there?
I'm here.
Okay, do you know what the next step is after we've done this?
Do we sketch?
Yeah, we're gonna do our sketch. So we're on the third step here. We're ready to do a sketch. So we're gonna start by putting our x-intercepts, then we're gonna put in our end behavior, and then we're gonna connect the dots, but we're gonna keep in mind whether or not we're touching or crossing, right? Okay, so Faith, I'm gonna draw you an XY axis here. And then I'd like for you to tell me what you'd like for me to put on here first. So what do you want me to do first?
We would put the 0 on the
Okay.
x-intercept axis. Sorry.
X-axis, I put right there, I put a blue dot there at 0. Okay, good. What else?
And then we'll put the 3.
At 3. So it doesn't matter how you want to count. I'll do 1, 2, I'll do 3 there. There, I'll put my second blue dot. Okay, good, Faith. Want to keep going?
After that, don't we just kind of like just connect the dots?
Okay, we will need to connect the dots. The problem is we don't know where to start from yet. Like where would I start drawing? Do I do this or do I come in from here, right? Like I don't know yet. So the second step is to use the end behavior. So remember, Faith, what did the first step of our work tell us about the end of this function? Both sides go up, right?
Yes.
Okay, so that I want to add to my graph. Before I connect any dots, on the left side, I'm just going to put my graph goes up here. And then over here, I'm put my graph goes up like that. Now you can start connecting the dots. So Faith, I'm going to stick with you here. I'm going to start connecting. So I'm going to start drawing. I'm going to use this piece here in blue. And I'm going to continue drawing it. And I'm going to head towards this first dot right there. Now, when I get there, Faith, what am I going to do? Am I actually going to cross through or am I going to just touch?
You're going to cross.
I'm going to cross. Okay, so let me do that. I'm going to go ahead and I'm going to cross through. Now, Faith, we have to connect to the next dot, which is at 3, right?
Yes.
And when I get there, am I going to cross or am I going to touch?
You're going to cross.
I'm going to cross. And then once I cross, you can see it pretty naturally connects up to this piece. So just connect them together. And that's it. We're done. That makes sense, everyone? Anyone have a question on that? So that's our answer. That's the picture. And I told you before that everyone's picture is going to look a little bit different. The thing I can tell you, though, is everyone's picture is going to have these two dots. It's going to have to go up on the left, up on the right. And in between these two dots, everyone's graph is going to go below. You know, someone might come way down here. Someone may just like skip across, but everyone's has to go dip down and back up. Let me show you something. Let's take this piece out. Okay. Let's just say that we had gotten to this step. I want to show you something. Let's say we had gotten to the step where we put our x-intercepts here. And let's just say for the sake of of demonstration that our leading coefficient test wasn't up. Let's say it was up, down. Okay, let's just say that's what it was. And now let's try and connect the dots. When I connect, I go to 0, right? And when I get to 0, I have to cross through. And then we already said at 3, I have to cross through. And now what? This doesn't make sense, does it? Does everyone see that if I were to continue, I have to get back down to this, which means that I would have to somehow turn and come back down here. Why is that not okay?
Because then it would have to have another X-intercept.
Very good. See, what you've done here is you've created an X-intercept that doesn't exist. So that can't possibly be right. So what I'm getting at is if you're sitting here doing this and you were to get to, oh, I don't want to do that. Let me do this instead. Let's say that you were doing this problem and you got to this step right here and you're like, wait a minute, what? You know, like, wait a minute, I'm here, but I've got to get down here. What that should tell you is either 1, you messed up the leading coefficient test, which means you have your left, right, you know, up, down, whatever, you got that wrong, or you've got your cross touch wrong. But that at least indicates that something's wrong. So you're going to have to go back up and just review everything. For it to go like it did for us, right, when we did the problem originally, everything worked out very nice, right? We had this piece here, we came through, we crossed, we connected, everything just fit together. And normally when you do the problem correctly, everything will fit together. So I guess what I'm telling you is be aware of situations when you're doing a problem. When things don't fit, then that usually means that something's wrong, all right? Okay, let's do another one. Give me just a second. I want to make this one up, but I want to make sure it works out right. Okay, yeah, this is it. All right, here we go. This one's going to be interesting. Okay, x to the 5th. This is about as hard as a problem that I would present to you, okay? I wouldn't give you anything harder than this. All right, here we go. Step 1. Lauren, are you around? Wait, Lauren, you asked a question already, unless you want to get us started here.
Yeah, I can.
Okay, so step 1.
The coefficient would be 1, so that one would be
So leading
positive.
coefficient is 1. What's the degree, Lauren?
5.
Degree is 5. And I think I hear you looking back in your notes there.
Yeah, I'm trying to find the table.
I'll bring it up for you. There you go. I'll let you look at that. So which one are we? Yellow, green, blue, or purple?
Green.
Green. Right? Everyone, we've got an odd degree and we got a positive leading coefficient, which means we're here. So the left side's going to go down, the right side's going to go up. Left side down, right side up. We don't know what's happening in the middle. Okay, good. All right, let's see who the lucky one is here. Ashlyn? Ashlyn, you here?
Yes.
Are you following along with everything?
Yeah, I am.
Okay, so second step, Ashlyn?
That's to factor to find the X-intercepts.
Yeah, okay, so this is going to be the most challenging part of the problem for most of you. This is going to go back to your comfort in factoring, which we haven't done a terrible amount of factoring, but it's something that we should all have some experience with coming into this class. But let's just kind of go through this and see what we can do. So Ashlyn, what's the first thing we do when we factor all the time? We talked about this last class. What do we always try first?
To find the most you can take out from the x.
Yeah, exactly, the greatest common factor. So Ashlyn, do you see something that all of these terms have in common?
X squared.
X squared, good. So I'm going to take that x squared, I'm going to pull that out, and I'm going to let Ashlyn tell us what's left inside, and then I'm going to cut Ashlyn off the hook here after this next step.
Okay, so x cubed
Good,
plus 5x squared
good,
minus 4x
good,
minus 20.
good job. Okay, so that part is a GCF factoring. Now, unfortunately, we could right now, because we have multiplication here, we could set this x squared to 0 and then set all of this crap right here equal to 0. The problem is all of this equal to 0, we don't have an answer to that yet, because we don't know. This is a big expression still. So we need to see now if there's any way we can factor this. And so that's my question to the whole class right now. Do you know how to factor something like this? Does anybody know?
Can you group it?
Group it, right? Good job. Who said that? Emily? So I'm going to put this on the side. So Emily said group it. So this is a technique of factoring that we use. It's called grouping. And we use this whenever we have 4 terms, which we have 4 terms here. Now, I know we've done grouping before because we talked about it when we were doing the AC method for factoring trinomials. So here we split it into 2 like this. And then from the first, all we do is we look at the first 2, right? So Emily, since this was your idea, what could we factor out of just these 2, Emily?
The x squared.
X squared. Okay, so if I pull just x squared out of those 2, what would I be left with, Emily?
X plus 5.
X plus 5. Okay, good. Now, you look at the second 2. I'm going to keep Emily on this here, then I'll. What are you going to pull out of these 2, Emily? There's something they have in common.
The 4 can go into the 20.
That's right. So they both have a 4, right?
Yes.
So I could pull out a 4. Now, if I pull out a 4, don't write this down if y'all are writing anything. Don't write this down. If I pull a 4 out of both of these, a positive 4, then I'm going to need to get a negative x and a negative 20. So I'm going to have a negative x here and a negative 5. And that's not going to work. The reason it's not going to work is because in order for grouping to work, you need this and this to match. So Emily, what could I have pulled out that would have fixed that?
A negative 4.
A negative 4. That's right. So we pull a negative 4 out. That leaves us with an x and then plus 5. So when you distribute the negative 4 back through here, you would get back these 2. Okay, does anybody else have a question about this grouping that we're doing here? All right, you sure? Okay, now, since these 2 things match, the next step is just to write that down in parentheses, write down the part that matches, and then in a separate parenthesis, you will put the 2 things that were out in front of it, in front of those 2 parentheses. You'll just put those 2 things inside of a parenthesis. So I put x squared and minus 4 in parentheses. So we've actually now turned this big ugly thing into something that's being multiplied, right? See that those are being multiplied? Now, looking at what we have here, does anybody see anything else that we can do? There's one more thing that we can do. Anyone see it? I'll give you the hint that the x plus 5 we can't do anything with. It has to do with this right here. Anybody recognize that?
Can't you square it?
Did you say square it?
Yes.
We could
Like-
square root if we set it equal to 0. This is something that we talked about in the past. I'm trying to think of what section this would have been in. Let me actually show you. This was back when we were talking about GCF. Hold on. I need to go back and look at the exact section. I don't know how far I want to go back and look. I'm really hesitant to go. Yeah, you know what? I don't want to start going through all of our old notes. This is a special factoring product. This is called a difference of squares. So what we have is something squared minus something squared. So this is x squared minus 2 squared, because 4 is 2 squared. You have to recognize that. And so whenever we have a difference of squares, that will always factor to be x plus whatever the number squared is, and then x minus the number squared. So let me try and show you underneath here. If we had x squared minus 1, this would turn into x plus 1 times x minus 1. If we had x squared minus 9, this would be x plus 3, x minus 3. If we had x squared minus 16, this would be x plus 4, x minus 4. So this is a special sort of factoring that we have when we have what's called the difference of squares. All of these numbers, 1, 9, 16, 4, those are all perfect squares. And so that's why we can break that down. Excuse me. So, with all of that said, this right here is what we have in that parenthesis. So I'm going to come back to the left-hand side and I'm going to write everything down. Any questions on that? I'm going to give you a problem. After I'm done with this, I'm going to give you a problem to work on to make sure that you can do this on your own. But does anyone have a question up to that point? All right, now we set each of these equal to 0. Set x squared to 0. Set x plus 5 to 0. Set x plus 2 to 0. Set x minus 2 to 0. And when we do that, we get a couple answers. First one is 0. Next one is -5, just subtracting 5 on both sides. Next one is -2, just subtracting 2 on both sides. The next one is +2, just adding 2 to both sides. Okay. Carolyn, you here?
Yes.
All right, Carolyn. I've found the x-intercepts. This is the points on our x-axis where we have dots. What do I need to look at next before I start graphing?
If they cross or touch.
Cross or touch. So can you tell me about what's happening at 0? Are we going to cross or touch here?
Cross.
Where are you getting that from?
Oh, wait. Hold on. Sorry. They would touch because of the x squared.
That's right. Okay, so because 0 comes from this factor, x squared, and Carolyn said, oh, wait a minute, that's a 2 up there. 2 means even, right? Even means you touch. All right. Carolyn, I'll let you do the next one.
Okay.
How about at -5? What are we going to do?
Would they cross? Because it would be 1.
Yeah, there's a power up here. This comes from this factor. That's a 1 here. That's odd. Odd means cross. And Carolyn, would you agree that the next 2 that we do are also going to cross through, because those are both 1s on there, on those factors also?
Yes.
Okay, so I like to do this. This is going to be touch, cross, cross, cross. That's what's going to happen. So at 0, we had an even power, we touched. At -5, we had an odd power, we crossed. -2, we have an odd power, we crossed. 2, we have an odd power, we cross. And now I'm ready to draw my picture. All right. How about Abby P? Abby P?
I'm here.
How do you say your last name?
Pockle.
Yeah, I'm sorry, if you don't mind me asking. It's just, I've
No,
never,
yeah.
I've never seen that last name, and it's just, I always
Yeah,
try
it's
too hard to
German.
pronounce things. What's that?
It's German.
Yeah. So how did you say it again?
Pockle.
Paco. Okay, I would have tried like CH, like Patchel or something.
Yeah,
like
like Patchel or Packle. Yeah, I get it.
that. Okay, anyway, all right, so what am I doing now? I forgot.
Let's see. So after we figure if we touch across, we're going to sketch it.
Yep. So what should I start with then on this sketch?
The X-Intercept.
Okay, so I'm gonna put, how many points am I actually gonna wind up putting down here?
4.
4 of them, right? So I've got 0, I've got one at -5. Got another one at -2. Another one at +2. All right. Now, what would you do next, Abby?
Let's see.
After you've got the dots down?
The end behaviors.
Which for us was down and then up, right? Down and then up.
Yeah.
So I'm gonna go to the left pretty far over here. I'm gonna just go down like this. Over here to the right, I'm gonna go up. Notice that when I put these like arrows here, I made sure that they were far enough to the left that I was to the left of the leftmost point. Like I didn't do it over here. Y'all see that? I intentionally put it way out here to the side. Same with the one on the right. It's to the right of 2. That way when I connect everything, it'll be nice and smooth. Okay, now we're gonna just start connecting. So I'm gonna start drawing. Abby, you tell me. Well, you know what, Abby, I'm gonna move on to the next victim here. Taylor, you're up. How's it going, Taylor?
It's going good.
Thanks for having your video on, by the way.
Mhm.
I guess you want the bonus points.
Oh, no.
Okay. So Taylor, are you following, first of all? Are you okay with this?
Yeah, I'm okay with it.
Okay, I'm gonna just start drawing, and I'm gonna start headed towards the next dot, and you're just gonna tell me when I get there what you want me to do, okay? So here I
Okay.
go. Go ahead.
You're gonna cross it
Okay.
and then go down. Cross.
What do you want me to do here?
Cross.
Cross, okay.
Yeah.
Then head back to 0. What do I do when I
Then
get there?
touch it.
Touch it. So when I touch it, that means I'm almost gonna kind of like bounce off of it
Yeah, and then cross it.
and then connect it. See how everything fit together?
Mm-hmm.
That's what you're looking for. So this was a cross, this was a cross, this was a touch, this was a cross.
So when you touch it, that just means like you're like bouncing off of it.
Like bouncing off of it, yeah.
Okay.
I say bounce or touch. Last class we said touch more than we said bounce, but I look at it like a ball bouncing off a wall is the way I see it. So Yeah, whatever, however you want to look at it. Okay. So this problem was, I don't know, would you agree that the difficult part of this is the factoring? Right, this part right here, because you have to know how to do grouping, then you have to recognize difference of squares. Yeah. Okay, so let me ask you, would you like me to give you all, let's do a poll here. Would you like me to give you a problem to work on, like in groups, or would you like for me to just move on to the next topic, rational functions? So yes, for let's do a problem together, or you do problems together. No, let's move on to the next thing. Of course, y'all are going to make this difficult for me. Okay. All right, that's good enough. So we have, surprisingly, we have more people that are ready for me to just move on. Now it's almost 50-50. Okay, so I'm going to go with the majority on this because there's enough people who are ready for me to move on. Let me put a problem up here just for you to practice on your own time. All right. Oops. Okay, so here's one for you to practice. F of x equals x to the 6th minus x to the 5th minus 16x to the 4th plus 16x cubed. All right, so don't do this right now, just write it down. And you'll want to maybe practice that for homework. And I'll give you a couple of other problems to look at too, but just that problem is very similar to this problem in the sense that you're going to have to do some grouping and recognize some other things. All right. All right. We are moving on then. So we're going to talk now about what are called question.
No, I didn't finish copying.
Oh, I'm sorry.
All right, thank you.
Yeah, no problem. All right, so we're going to now talk about rational functions. Now, just as a reminder, here's what we've done. Again, in this class, we have done linear functions. Those were lines. We've done quadratic functions. We have now done polynomials. I'm just going to put poly, and now we're talking about rational functions. Linear functions, we've already had a test on, okay? So your next exam is going to contain quadratics, polynomials, and rationals. That's going to be on exam 3. In fact, that's most of what, I mean, that's all of what exam 3 is going to be about, is quadratic, polynomial, and rational functions. So this is kind of the last topic that we have before our next test. But I will tell you that this is the hardest topic, all right? This is the most difficult of all of the functions that we will ever do in this class. Rational functions are the most problematic, okay? They have the most stuff happening, and they're the most confusing. So we're gonna just do the best we can, all right? I'm gonna try and present it in a way that makes sense, and we'll have a set of steps, and we will go through the steps and see how it goes. Now remember, on exam 3, I told you I'm going to allow you to have a cheat sheet, right? We're going to allow you to have a sheet where you can put all the steps. So you want to make sure that you're writing this stuff down in your notes so that when you go to make your cheat sheet, you have a good place to reference. All right? Okay, so rational functions. What is a rational function? What do they look like? Well, they're actually very simple to define. A rational function is a polynomial. So we just studied polynomials, right? We just studied what a polynomial is. It's a polynomial divided by another polynomial. So it's not just a polynomial by itself. You're taking a polynomial and dividing it by another polynomial. You're creating a ratio of two polynomials, which is why we call them rational functions. It comes from this word ratio, ratio meaning fraction. So this is a fraction made of polynomials. Ugh. All right, let's take a look at a couple of examples of rational functions. So here's an example of a rational function. X plus 1 over x minus 4. Now, notice that the numerator, that's the top, the one in yellow, is a line, right? But we said last class that lines are polynomials. The lines, what is the degree of a line? What's the highest power of x? 1, right? So a line is a polynomial. So we have a polynomial and we're dividing it by another polynomial. And the question would be, what does the graph of this look like? Okay, so that's one example. Let me give you another example. I'll call this one g of x and I'll do a different color. How about we have, again, let's just put that x plus 1 up there. So it's the same up there, but now on the bottom, let me do x squared plus 5x. So now, do you see that the denominator is a quadratic instead of a linear? So you still have two polynomials, polynomial divided by a polynomial, but the bottom is different, right? It's not linear, it's not a line, it's a parabola. And then let me give you another one, h of x. How about I take the problem we just did there, g, and what if I flip it over? Like put the quadratic on top and put the linear on the bottom. That's still a rational function. These are all examples. Do y'all see that? Like I could just keep going like for the rest of the day, writing examples of these down. Like it's like any polynomial you could think of divided by any polynomial you could think of. Now, we're going to keep, I'm going to keep it simple here, right? I'm not going to get crazy. I'm not going to put like, I'm not going to give you a problem where I put like this right here. I'm not going to give you that and then divide that by something just as big and ugly. All right, that's not going to happen. I'm going to keep it very basic. It's going to be, you know, linear stuff and quadratic stuff. That's about it. I'm not going to go any crazier than that. All right, that'll help you. So what do you say we take a look at the graphs of these? All right, let's go look at the graphs and let's see what they look like. We know that they're not lines. We know that they're not parabolas. They don't look like little U's. Well, we don't know if they look like polynomials yet. We haven't looked at them, but would you all agree that a polynomial, like all the polynomials we have graphed have looked kind of like, I don't know, like little roller coasters or something? Just nice, smooth, curved, right? I wonder if these rational functions will look like those. I don't know, we'll see. So let's get to this graphing software. I'm going to type in that first one. I've already forgot what it was. X plus 1, oops, I need that in parentheses, divided by x minus 4. Let me just write them all down first, and then we'll go look at them. X plus 1 divided by x squared plus 5x. And then the last one was that same thing, but flipped over. X squared plus 5x divided by x plus 1. All right, y'all ready? Holy shit, right? Like what a mess. Like none of this looks, like none of these look the same. Like, would y'all agree? Like they all look just completely chaotic and random. So like there's the red one is the first one. This is x plus 1 over x minus 4. There it is. Definitely not a line, definitely not a parabola. It doesn't even look like a polynomial. It doesn't even look like something that's nice and smooth and curved. It's like weird, right? It's got this weird thing happening here. Strange. And then this next one, look at that one and take the red one out of here. Look at that. That's got all sorts of weird stuff happening, right? Again, not a parabola, not a line, just strange. And then this last one, again, that doesn't look like a line or a parabola, but all of them together, like they're all different from one another. Do y'all see that? Like, even though these are all rational functions, they're all very different from one another. So this is what makes rational functions challenging, is that you don't have like a basic, like, oh, they all look like this, they're just a little different. No, they're all different. So this is going to be interesting, right? It's going to be interesting how this works out. Now, before I get into this, I want to do something which I forgot to do last time. Maybe this will help out. So we're going to take a quick little pause here. Do you remember when we started talking about quadratics and parabolas? I gave you a bunch of real world examples of where we use parabolas, right? I gave you, like, satellites and mirrors or headlights and all this different thing. And I was trying to convince you that parabolas were important. Well, polynomials are important also, but we just got finished studying. Polynomials are great at modeling things in the real world that, change, that go up and down. So you could be thinking about, anything that just kind of fluctuates over time, whether it be, I'm just trying to think of stupid examples. The money that you have in your bank account, right? You get paid, it goes up, it comes down, you spend money. The stock market, the temperature outside. I mean, anything that goes up and down, polynomials are wonderful for modeling those real world situations. And if you notice that if you have something that goes up and down like this, a line's not going to work for that. So you can't model something like that with a line. You can't use a parabola, because parabola is either just, parabola just does that. So you need something that fluctuates, and polynomials fluctuate. So they're really good for that. Rational functions are good for something else, something specific, and I want to point out what it's good for. So I'm going to give you a quote from a movie. I'm going to see if anyone in the class can tell me what movie this quote's from. I'm just going to type it in here, and I'm paraphrasing. I might be off a little bit here. The quote is something like this: "On a long enough timeline, the survival rate for everything drops to 0. Does anybody know what movie that's from? Any guesses? No? I'm sure you could Google it, but the actor that said it is actually Ed Norton Jr. He was in this movie with Brad Pitt. No? No? Okay. Fight Club? Has anyone ever heard of that movie? Fight Club. Yeah? Okay, maybe not.
Yeah, I've heard of it.
Okay. Now, I'm not sitting here promoting the movie. I'm just saying that's a quote from it. So in this movie, the main character he works for an insurance adjuster. And they're talking about how insurance companies figure out how much you have to pay for insurance. And one of the things he says in the movie is, on a long enough timeline, the survival rate for everything drops to 0. Now, look, this movie has really nothing to do with insurance and math. If you watch the movie, it has to do with crazy stuff. But that's an interesting quote, because that's exactly what a rational function is. So I'd like for you to consider something. I want you to think about this deeply. I'm going to put a timeline here. Okay, so this is time. And let's say we're going to measure this in years. And over here, our y-axis is going to be the probability that someone is alive. Okay. So just think in general, just think about a human being on this planet, all right? So let's say we start at time equals 0. And that would be, I guess, when this person becomes alive. And man, I can't even imagine the sorts of debates we could have right now about when life begins. We are not even going there. We're just going to all say that whenever life begins, whenever that is, whether it be when you're born or conception or whatever your own belief is, who cares? Let's just say whatever that is for you, we're going to call that time 0. You've got this person that's now alive, okay? So the probability that they're going to be alive is 100% at the time that they are born or become alive. Now, as time goes on, what's the probability that they're going to still be alive? So at time equals 0, we know they're alive, so it's 100%. Now, what do you think the probability is that they're going to live to see their first year of life? Do most people that are born live to see 1 year old? A lot of them do, right? I would say, you can't say 100% because some infants do die. So we would put it as a high probability, maybe, and I'm just making up these numbers. Maybe it's like 99%, all right? Now, how about the probability that they'll live to be 2 years old? Well, I don't know, pretty high still, right? Now, let me move on down the timeline. Let's move to 50 years old. Now, what's the probability that a person's going to live to be 50? Do you think that that's, most people do live to be 50? Yeah?
Yes.
Any feedback you have, I'd appreciate, because I really want to know what you think, especially as I keep going down this timeline. So would you say that you have like more than a 50% chance of living to be 50? Like, at least in America, right? In the United States of America, we have relatively decent healthcare. So the average person is probably going to see 50 years old. But,
Yeah, that sounds fair.
you know, I mean, 50%, I would say you have a better chance than a coin flip that you're going to live to be 50. So it's still going to be pretty high. All right, let's go. How about 75? Well, now this also does depend on whether or not you're a man or a woman, because women on average live longer than men, right? That's been documented. Not sure what that is, why that is, but sure we could debate that too, right? Okay, but would you still say it's greater than 50%? I'm seeing a shake of head no here. I'm gonna agree. I don't know if I would say, I don't know. I don't know, but it's starting to go down. So let's get to a number that really starts to make you think. Let me get rid of this here. So how about 100? What do you think the probability is that you're going to live to be 100?
I would say at least, I mean, 15%. I don't think I know a lot of 100-year-olds.
Yeah, I mean, it happens though, right? People do live to be 100. My wife's grandfather is 102. You
My
know.
grandma's 90.
Well, what was that? Abby, what did you say?
Sorry, no, I'm talking to a kid.
Okay, so some people do live to be 100, but I don't think there's a whole lot. Okay, I mean, it does happen. All right, here's where things start getting interesting. How about 120? What's the probability that somebody's going to live to be 120? Now we're talking about probabilities here. Like, so my first question would be, could it happen? I mean, could it happen? I mean, I don't know. I don't know what the world record is for the oldest person, but it is possible to live to be 120. I mean, like I said, my wife's grandfather is 102. So could he go another 18 years? I don't know, maybe, right? Maybe. So we would have to give it some probability. That means we couldn't say 0%. We cannot say 0%. It has, there is some slight chance that someone could live to be 120. Okay, so now we're going to go like even crazier. How about 200?
0%.
0%. You sure?
I don't think I've ever heard of anybody living past like 120 something. So I would say 200 is a pretty safe bet that.
Okay, so I understand your argument. Like nobody's ever lived to be 200. But if you're going to say that the probability is 0 to live to be 200, right? If that's what you wanted me to do there is actually make that 0, like put a dot on the x-axis like that. Then how about 199? Is that 0 also?
Yes, I think I mean something fair that we could do is
Mhm.
what we could do. I mean, what I would have done if this was like a real study or something, and was like actually like look up like the oldest person in the world, or like what was like who was the oldest person, and then like after the age of death, I would do any age after that, probably like 0% because nobody else has matched.
Okay.
The oldest
So
person, I got the actually have that. The oldest person who lived to be 122 years old and 122 years, 164 days old.
yeah. So I understand what you're saying. We could go and just say who's the oldest person, and then we could say that's where we go to. That's where we say 0. The problem with that is we're talking about probabilities. So a probability is you're trying to predict events that have not occurred. So like right now, if I tell you that I'm going to flip a coin, what's the probability that I'm going to get heads? 50%, right? Right? Now, let's say I flip a coin and it comes up heads right now. I can't use that result to say that every time I flip a coin, it's going to be heads. Does that make sense? Like, you can't look at the oldest person and say that's the maximum anyone can ever be, because you're looking at one specific example as opposed to a probability which is supposed to predict what would happen. Let me phrase this in a different way. I think it's very unlikely for someone to live to be 200 years old. I think it's very unlikely, but there is still a chance. There's a little tiny chance. So I'd like for you to consider this. I'm going to give you 2 scenarios, and I want you to tell me what is more likely to happen. First scenario, somebody lives to be 200. Okay, that's the first scenario. Here's the second scenario. I'm going to go play the lottery tonight. Okay, I'm going to play the lottery tonight. And I'm going to win it. Which of those 2 is more probable? What do you think is more likely to happen? Me living, or someone living to be 200, or me playing the lottery tonight and winning? What do y'all think? What's more likely?
Living to be 200.
What's that?
Living to be 200.
You think that's more likely?
Unlikely. But then it's like very unlikely. It's so rare
What's rare?
for like someone to like win the lottery. Because like I mean like, yeah, like you can win the lottery, but maybe not a lot of money.
Yeah. So, but I could win, right?
Yes.
Like I could win. People do win the lottery.
Yes.
We have examples of people who win the lottery. We have no examples of people who have lived to be 200, right?
Yes.
But this is probably more likely, right? That I win the lottery than I live to be 200,
Yes.
right? Okay. Now, what if I tell you, not only do I go tomorrow or today and I go win the lottery, on my way, walking out from the gas station where I bought the lotto ticket, as I'm walking out, I get hit by lightning and I live. Okay, so then I get hit by lightning. And I live. All right. Now tell me, could I go play the lottery today and win? Could that happen? Yes.
Yes.
Could I walk out, get hit by lightning, and survive? Could it happen?
I mean,
I'm
I
not-
guess so, but I mean, the weather conditions aren't really,
Okay. I agree the weather conditions aren't really likely for it, but could it
Yes,
happen?
but it is possible.
It
Yes.
is possible. You can't tell me that it's 0% chance. You have to give it some small probability. It might be 1 in a trillion, but it's still something, right? Now, which of those is more likely? Lottery, win, hit by lightning and live, or live to be 200? Well, then you start to wonder which is more likely, right? And then if you still think it's more likely for me to do this, get the lottery and get hit by lightning, what if I say that this happens to me 3 days in a row? That means I go play the lottery today, I win, walk out, get hit by lightning, survive. Tomorrow I go play the lottery again, win, get hit by lightning, survive, and I do it 3 days in a row. Again, could it happen?
Yes.
You can't say no. You cannot say 0. You can't. Okay, you can't, because it's possible. And if it's possible, then it has to have a probability. It has to have some chance of happening. But we're talking about odds that are so slim, so small, that they're practically 0. So what I'm getting at is this curve that we have that's talking about the probability of someone being alive. What it's doing is it's dropping down and it's getting closer and closer and closer to the x-axis, but it's never actually going to get to the x-axis. It's just going to get closer and 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 never, ever, ever touch. And if you go back and you look at this graph, this red one here, you'll notice that that's exactly what's happening. The graph is dropping down. Notice that it's getting closer to the x-axis. I'm going to zoom out. As I get further and further out, it gets closer and closer and closer and closer. And I can just keep going forever and ever and ever and ever. And it's going to be that you're going to have it. See, yeah. So, why is that showing? Oh, okay. So it's getting closer and closer. Do y'all understand that? We have this very strange thing happening. Try and zoom in on this. Come here. There we go. We've got this strange thing happening where the graph is dropping down, getting closer and closer to something. And that's exactly what Ed Norton Jr. was saying in Fight Club. He was saying on a long enough timeline, the survival rate for everything drops to 0. So on a long enough timeline, if you let this timeline keep going out, forever, 100 years, 200 years, 300 years, 1,000 years, 1,000,000 years, the survival rate for everything drops to 0. It never gets to 0, but it drops to 0. You can also think about this. This is used in the real world in things like companies that make, like let's say you make a car, like let's say you manufacture, or let's do cell phones, okay? Because we all have cell phones. So what if we have time and we have the probability that your battery is still working, right? Because the battery in a phone is probably the weakest part of our phones, right? All of our cell phones, the one piece of our cell phones that is the weakness is the battery. Your phone will keep working, but your battery starts to go, you can't replace it easily, at least. They have to take the phones apart. And that becomes more expensive than actually just getting a new phone. So they build these phones in a way that they make the battery just enough to last for how long they think you're going to keep the phone. Like they think, okay, every 2-3 years, you're going to want to get rid of this and get a new one. So what they do is they make a battery where on the beginning, it's going to work, but they want this to drop down. Well, actually, they don't want it to look like that. Let's say here's like 1 year, 2 years, 3 years. They manufacture it so that the probability that it's alive or that the battery is still working is pretty good in the first 2 years. And then what starts to happen is it drops down And then you start to have that thing that just happened where you're getting closer and closer to 0. But you want it to be pretty reliable, pretty good chance of living the battery working for the first few years, and then later on, if it drops down, drops down. This is an example of a rational function. Okay, so hopefully that makes some sense in terms of like where we might see these in the real world. They're used all over the place. What we need to get to now is how in the world are we going to sketch the graphs of these? So what I'm going to do first is I'm going to write the steps down. We're almost out of time, so we're not even going to get to an example. I just want to lay out for us for next class what it is that it's going to require to sketch these. All right, so the first step of sketching these, so steps to sketch rational functions. Okay. The first step is we're going to find what are called the X-intercepts. We've already found X-intercepts before, right? But with rational functions, we only have to do one thing to find the X-intercepts. We just have to set the numerator equal to 0. So we set the numerator equal to 0 and we solve. Remember, the numerator is the top, okay? The numerator is the top. After we do that, we are going to find what are called our vertical. So vertical means up and down. Vertical, this is a weird word. Vertical asymptote. Vertical asymptote. Don't try and pronounce it. Just say it real fast and no one will know you're messing it up. Asymptote. The M's kind of silent and the P's kind of silent. It's like asymptote, asymptote. The M's in there, yeah, whatever. We find the vertical asymptote. Now, to do this, we will set the denominator equal to 0. Now, I haven't talked to you about what this is, okay? So right now, you don't even know what a vertical asymptote is. You know what an X-intercept is. Those are dots on our X-axis. But a vertical asymptote, we will discuss next time. I'm just giving you the steps. The next step is that you will have to find what's called the horizontal asymptote. And to do that, you will have to compare the degree of the numerator versus the denominator. Again, you don't know what a horizontal asymptote is right now, and don't worry about this right here. It's just when I come into class next time, I want to be able to put these steps up and just be like, okay, this is where we were. Let's now talk about what a vertical asymptote is. Let's talk about what a horizontal asymptote is. Let's talk about these steps. Okay, so we find the X-intercepts. We find the vertical asymptote. We find the horizontal asymptote. The next thing we do is we plot all the information we have. From steps 1 through 3. So what we're going to do is we're going to put all that information that we just gathered onto a graph. Once we put all that information onto a graph, we're going to pick test points and then the last step will be to sketch. Okay, so this part, picking test points, you have no idea right now what I'm talking about, all right? So don't stress out about it. These are the steps to sketch a rational function. We will go through this in detail on Tuesday and hopefully be able to get through a few examples to get you ready for the test. And on the test, we will see, it depends on how much we get through. I might make rational functions just a bonus problem because we're going to finish it on Tuesday and then your test is on Thursday. So I'm really thinking that the test will be mostly quadratic and polynomial, and then with a bonus with rational. I think that that's probably the most fair way to do this. Okay, let's call it a day. What I'm going to do is I'm going to send out a review. Okay, I'm going to send this review out to you in the next day or two. Let's see, today's Thursday. Actually, I'm going to have to send it out either today or tomorrow because I'm going out of town this weekend. So I will send you a review. That review will be a homework assignment. Just, I mean, you're not going to turn it in, but you know, if you want to have homework to practice the polynomials and stuff, just do the review. That's going to be a good practice for you. And that will also prepare you for the exam for next week. Any questions?
I'm good, thank you.
Okay. Have a great day, everyone.
All right, thank you,
Great
sir.
weekend.
Thank you. Have a good day.
Have a good one.